Oh, hell yeah. Now, we already did this problem with numbers, and I don't want to read it through either. But anyway, it says, hey, this is the equation for how long the yellow light should be. And it's like, prove it. You know what I mean? Did we do a good job? Did we write a textbook that don't have no errors? Of course you did. You know what I mean? Because you made, it's the same textbook since 1950. Probably 1930. It's literally the same problems. Alright, but anyway, you have a yellow traffic signal, and it's got to go on. And, well, what time? You know what I mean? So here you go. They say, hey, you have a reaction time, and so here's the intersection. They give you its length. Well, actually, in the next problem they do. But anyway, so it does have a length, and then you have, and it says, yeah, you have a reaction time. Now, I know I wrote this in here, but we don't even need to. This was 1.1 from the last problem, but it's just the time it takes to actually react. So you're going at a certain speed. Now it can be any speed. And so you have this distance that you travel because you can't react, you can't put your foot on the brake. Now what's this distance? Let's make it real easy. If your velocity is like 10 meters per second, and this your reaction time is 1 second, well, that's going to be 10 meters. So meters per second times time is the distance. Okay, and yeah, well, let's just go right over here, because I didn't even put it in. But this literally should be the king, you know, one of the king of equations. We'll just say 0. This is the king. Acceleration, change in velocity, change in t. Velocity, change in distance, change in t. We wanted to find the change in time. So yeah, we took the distance divided by the velocity. Or what the hell did we want to find? I forget. No, we knew our reaction time. And, oh, so if we knew our reaction time and we knew our velocity, you could find change in x. So let's write that one in. Change in x is velocity, change in t. Okay, so that's how we actually got, we knew this distance now. Okay, because that's what we want to know. We kind of want to know this distance. We're going to say this is the distance for our reaction time. So distances are s. The reaction times, or the time it takes you to brake, this is your time braking, time accelerating, reaction time, and then we'll get to this intersection piece first. But basically, right here we got it all set up. If you see the yellow light right at this point, you're going to be going with a certain velocity. Times your reaction time is going to be this distance. You're going to get to here and apply the brake. And then you're going to get to here and you're going to be stopped. And you're going to be right before the intersection. This is the closest call you could get. Okay, fair enough. So what's this distance now? You were going in with some sort of speed, and then you stopped. And then even if we just know this, let's say we just know our time to brake. We actually had a stopwatch, and we're just like, oh, okay, so we clocked it. Well, over here again, I know it's kind of confusing. Let's go to our equation. We wanted to find, what the hell did we want to find? Oh, we wanted to find the distance. Yeah, the distance was the velocity times our reaction time. So now we're just going to say we know the time for decelerating. So same thing. This distance is going to be velocity times that time we clocked, our deceleration time. Okay, but the only thing is that in this one, in our reaction time, we're just going the same velocity. We ain't applying the brakes. But here, we start with a velocity and end with 0. So we need to take the velocity kind of right in the middle, or the average velocity. And since we slowed down at a constant rate, it's because acceleration is constant, is that the velocity average is just right in between them. So that's going to be v naught over 2. That's where this term comes in. So now this distance right here is this term that we don't know, but we calculated it. We know that we have to have a change. We have to have a time that we're decelerating. We clocked it. We came to a stop, and then you multiply that by the average velocity, and you get this distance. So SA is this time change in TA times v over 2. So do I even have that up here? Well, let's see. See, SA right here, I have negative V naught squared over 2a. So why is it so confusing? Well, right here I wrote it in. So that this is why you got to start with the simple stuff. This distance right here is your average velocity times this change in time for your braking. Now, what is the time it takes you to brake? Well, that's why I would go back to, we're going to throw some more time on the clock. All right, hell yeah. That's why I would go back to this king of equations. Acceleration, change in velocity, change in time. And this is a full-blown equation because acceleration is constant. If acceleration is constant, hell yeah. Change in velocity, I mean, this is just an equation. So we're going to rearrange this to get our change in time. So change in time goes up there, acceleration comes down. That's what I did there. And then we're just going to call it change in time for braking. Perfect. So change in time for the braking part is going to be your change in velocity divided by the acceleration. Okay. So, and then let's go back, not to confuse, this distance right here is once we know this change in time due to the acceleration, voice crack, multiply it by this V naught over 2 because we need the average velocity. That you just have to like throw out of thin air. You have to know this. That if you start with a velocity and end with 0, your average velocity is going to be split right in the middle. It's going to be this initial velocity divided by 2. Half the velocity going in. Got it. So again, this distance, V average times that change in time. But up here, we're trying to find the change in time. So this is our distance. Yeah, we know one part of it. We know we're going to use this V naught over 2. That's going to be that component. But we really don't know. We don't have a stopwatch. But somebody says we know the acceleration. Okay, cool. And we do know the change in velocity because we come in with an initial velocity and we end with 0. So our change in velocity is, and then let's look at that. What is change in velocity? Change in velocity is always V final minus V initial. Well, V final is 0. So our change in velocity for this problem is negative V naught. So that's why this negative always pops up, negative V naught. Anyway, negative V naught, and then we'll get why it's squared up here for our stopping distance. But anyway, okay, so now you have this, change in velocity over acceleration. Bring it down here. Velocity final minus velocity initial over acceleration. There's no velocity final. So there you go. Change in t is V naught, negative V naught over A. Okay, perfect. You found it. So let's put that into this equation. And now we're going to have V average, which is V naught over 2. And then multiplied by this, you're going to have negative V naught over A. That's where you get this negative V naught squared. I think... Do you have to write this like this? Yeah, you basically have to write it like this. It's the V naught. Oh, it's the V naught squared, and then you make it negative. So definitely, it's not just always a positive number. But anyway, that's the subtlety. All right, so we finally found this distance. We finally got a full SA. SA is negative V naught squared over 2A. Cool. And again, like this should be LOL. I guess it's just supposed to say or, but it's also the component of this velocity average times this change in time. And again, what the hell was change in time? Well, it was this. And then that's what we put in. Okay, so we know this distance. We know this distance was just given. The intersection is just a certain length. Okay, why is this useful? Why did I write all these down here? Is because, well, I guess we just needed to figure out these two distances. We saw the light. You can't do crap until your foot hits the pedal. Your foot hits the pedal, and then you go a certain distance. So once we know our stopping distance, because we're human and our car has brakes, this is the distance that it takes to friggin' stop a car going at kind of the normal speed. So we saw the yellow light right here. Okay, so now... Can't we just figure out that? Doesn't that give you the time? What the hell does that give you? Oh, it does. It gives you the, okay, so you could figure out the actual time that this whole process takes. And from the other video, this process takes like 9 seconds, you know, given the problem diameter parameters. Like literally the second you see the yellow light, by the time you're here, it's going to turn red, but you already made the decision. So now we get into the logistics of a car. You need this reaction time. You can brake. So this is the point where you can stop. I can stop. Okay, and but right here, just your car is just like 1 millimeter forward is the position where you can't stop. I can't stop. I got to get all the way through this intersection. So it doesn't make the yellow light go on longer. You actually get less yellow light because you are slowing down. This took like 9 seconds in the problem with numbers. But if we just say, hey, I ain't stopping, I'm getting through, this will take 6 seconds. Now here's that. Here's why. Is because you have an initial velocity and you got to travel this distance. So this SA and SR were important because now we know our reaction time distance. We know our stopping distance that it would take our car to stop. And then we know the length of the intersection. So the time it takes, so let's go back to this equation. What the hell is the time? Well, it's this distance divided by the velocity. So that's why I just wrote it like this. Our change in time is our distance. This is total distance divided by the initial velocity. We're going to have our initial, we're not going to do crap once we see that yellow light. We're just going to be like, hell, we're not going to motor it. We're just going to go the same speed limit. And we got to travel all these distances. And that's why it's SI, SA, SR divided by V naught. Got to throw some more time on the clock. Alright, hell yeah. Now the only thing that's different is I wrote them in opposite order. So here's the SI part. This is SI over V naught. This is the SA over V naught. And this is the SR over V naught. Excuse me. Alright, so this looks tidy, you know what I mean, tidy-whitey. Hell yeah, we got this. So how the hell do we go from here down to here? Well, for the SI over, the length of the intersection is just the length of the intersection. That's just a friggin' constant divided by the initial velocity. Hell yeah, that's that component. Now, let's do this reaction time, because that's the distance of your reaction time divided by the V naught, and that's just going to be your reaction time. And again, let's go back to this change in time. Change in time is your change in distance, SR, divided by the velocity. Okay, so that component is just change in reaction time. And because this is usually just a given, a human parameter. What's a human parameter's reaction time? 1.1 second. That's why they put it in that, because that's going to how it's, you're going to look it up in a psychological chart of people's reaction times. Got it. How about this middle? This is going to be SA over V naught. Well, what the hell is SA? SA is negative V naught squared over 2A. And then we're going to divide it by V naught. So we actually get rid of one of the V naughts. So now it's just going to be negative V naught over 2A. Negative V naught over 2A. So hell yeah, we did it. And then right down here I just kind of did that. So we have SI over VO minus V naught over 2A plus SR over V naught. And I just show that SR over V naught is just reaction time, because this is a human parameter. It's not you would put this first. You would get rid of, just put that parameter in. But hell yeah, we did it. We did a proof of why you have this formula for a yellow light. And yeah, this is difficult. I had to do the one with numbers first before it made sense to actually come back and do a proof. And I thought I could whoop this out in 5 minutes, but no, it's the same amount of time. All my videos take about a half hour. But this one was a little bit shorter, you know what I mean? Because I already wrote it, and we're just kind of going step by step through it. And I drew a nice little picture. Took my time. So I hope you appreciate that, and thanks for joining me. And guess what? That's a video.